Okay, in this video, I'm just going to state and prove a theorem that relates the density functions of two random variables that are related by a function. So remember that a random variable is a function, and so if you apply a function to it, you get another function, which is another random variable. Of course, the random variable is not just any function, it's a certain type of function, but if you have a function f, you can apply f of x, and f of x will be another random variable. And the question is, how did the density functions of those two random variables relate? So the theorem is, suppose that x has density function f, and that the values of x go from a to b. That's the probability that x is between a and b is 1. Let r be continuous and strictly increasing. So here I'm using the notation, it's kind of vague, but it's the domain is the open interval from a to b, and a and b can be positive and negative infinity. And let r go from the interval a comma b to the interval alpha beta. And I should probably indicate that this is a surjective map by using the two arrows. Okay, so this is a typical notation. So this is a surjective map. So let r be continuous and strictly increasing, and let capital Y be r of x, and let s be the inverse of r. Then y has density g of y, which is f of s of y times s prime of y. Okay, so the proof of this is pretty simple. So the idea is to use the cumulative distribution function. So let capital F of x be the probability that capital X is less than or equal to little x. Okay, well, we have that the probability that capital Y is less than or equal to y, right? So we're trying to take the derivative of this. This is the probability that r of x is less than or equal to y, and that's the same as the probability that x is less than or equal to s of y. Okay. That's because r is increasing and s is the inverse of r. So, and this is equal to f of s of y. So now we take the derivative of both sides. So g of y, the density function, that's the derivative with respect to y of the probability that capital Y is less than or equal to y. So by what we have, that's the derivative of capital S of s, and then by the chain rule, this is just f prime of s of y times s prime of y. And so capital F was the probability that capital X was less than or equal to x, so then the derivative is just little f, right? So this is going to be little f of s of y times s prime of y. And that's the proof.